Hello, this is Dr. DA, and this is the third video. In this one, I'm going to walk you through a set of calculations for experiment 5, molar volume of a gas. If you remember, we are studying the reaction where potassium chlorate decomposes into KCl and oxygen gas. Now, what we're doing here is we are not doing this reaction with pure potassium chlorate, but with a mixture of unknown composition. The reason is that in that mixture we also have this other compound, manganese dioxide, which, as we explained in the intro, behaves as a catalyst. It helps the reaction move along. So one of our first objectives in this experiment, remember, is to find out, well, what is the percent composition of potassium chlorate in that mixture of unknown composition. The second thing we're doing is we're going to take our gas product here and we're going to determine experimentally several things: the number of moles, the pressure, the volume, and the temperature. But we're going to do this under our lab conditions. And then we're going to use the combined gas law to find what is the volume of this gas. I'm sorry, I lost my place here. Okay, here we go. Let me get this out of the way. We're going to use the combined gas law to find the volume of oxygen at STP, standard temperature and pressure, which for us, we're going to represent as 0 degrees Celsius and 1 atmosphere of pressure. So that's what we're going to be calling STP, standard temperature and pressure. Okay? So if you remember, the way we conducted the experiment was we set up this apparatus that I showed you in the previous video how to do it. Our potassium chlorate is going to be heated, and as it heats, it produces oxygen gas. Oops, I'm sorry, I got some weird stuff here. Produces oxygen gas, oops, which then emerges into this reservoir here, where it causes water to get displaced through this delivery tube, and it then emerges into this beaker where we're going to collect it, right? After we have finished the reaction, we said that we typically have the water in the beaker and the water in the flask at different pressures. So the thing that we did was we equalized the water levels here, right? Because when we do that, the pressure inside our flask will equal the pressure on the outside. And that is the pressure that we are going to be able to measure. This will be the pressure of the air. The other thing we said we would do is we would measure the volume of displaced water here. And we're saying that however much water was displaced, that space is now occupied by the oxygen. So this will be equivalent to the volume of oxygen. We also measure the temperature of the water in the flask, and because of rapid energy exchange, that should be equal to the temperature of the oxygen. A couple of things. One of them is what we really need is the pressure of the oxygen alone, and as we're going to see in our calculations, that's going to require that we make some adjustments. So we'll have to adjust this to find the actual pressure of the oxygen. Also, the question came up in our demo: how do we find out the number of moles of oxygen gas? Well, for that, we are going to rely on the stoichiometry of the reaction. Okay? So we are set up. So what I'm going to do next is I'm going to show you a sample set of data by a former student of mine, and this was Susan. She had a younger brother, Johnny, who was my student later on, and very smart young woman. She had this kind of interesting quality. Every now and then, you would look where she was, kind of like she wasn't there anymore, like she was almost invisible. And then you look again, and there she was. So anyway, that was one of my former students. And as you can see here, she collected data similar to yours. I hope you remember to write down what your unknown number was, or alternatively, perhaps your instructor did not give you the unknown number, but they recorded it on their roster. So either way, the idea is your final result should match close to what the real values should be for that unknown. Okay? One of the things that I do here is, before I do my calculations, is I like to put numbers on these items. So I'm going to put numbers here. That'll be number 1, 2, 3, 4, 5, 6, 7, 8. Notice that Susan had here the mass of the empty test tube, and then the mass of the test tube plus her sample. And then after the first cycle of heating, she had the mass of the test tube plus her product. And then she had the same result, the same entry here after the second round of heating. Because those were, and I'll show you later, within the limits that we established for heating to constant mass, she was not required to do a third round of heating here. Again, the pressure, let me remind you of how we measure the pressure in this experiment. Let me see if I can find my barometer here. Here it is. Okay, so this is our barometer. And as I explained earlier, the outside scale of the barometer is given in centimeters of mercury. Oops, let me get that out of the way. This is in centimeters of mercury. And so we had to convert it to millimeters, which is torr. You can see we're between 76 and 77, for example. There are 10 intervals. So that means that the scale is calibrated to 1/10 of a centimeter. And because it is a graduate scale, as we were instructed, we have to add one more decimal. So right now the needle is right sitting on the 76.3 interval. So we're going to say that, let me put this a little bit smaller here. Okay, and let's say this is our reading here. Oops, sorry, I've got some kind of weird things coming up here. All right, so here is our reading here. So we would say that that was 76.3 centimeters, but we have to add one more decimal, so that'd be 76.30 centimeters, which means that when we convert that into millimeters, that would be 763.0 millimeters. So you should have recorded your pressures to 1 decimal of a millimeter. Okay? So let's come back here to our sample data sheet. We're back in here. And so what I'm going to do now is I'm going to walk us through some calculations. All right? I'll display some of them, but not all of them. I want to put these on a separate piece of paper. This is going to be my calculations worksheet. And remember that the idea here is that if somebody from the outside comes in, you want them to be able to follow along what you did. So this should not be just like chicken scratch, right? It should be fairly well organized. So I'm going to put here my, I'm going to put here my calculations. And I'm only required to show the calculations for one trial. So I'm going to show here, I don't know why this is happening here, for trial number 1. Of course, you'll have to do calculations for both trials, but you're only required to display one set. The first one I'm going to do here is I'm going to make sure that we did heat to constant mass. So I'm going to put here heat to constant mass. All right. And to do that, I'm going to compare the values she had here in item number 4 and item number 3. These are the 2 rounds of heating, right? So item number 4 minus item number 3. So those numbers that she had here were 23 point, I don't know why it's doing this. Kind of weird. 23.5736 minus 23 point, 23.5732, and I don't know why this is doing this, but hey, this should be equal, oops, this should be equal to 0.0004 grams, which is the same as 0.4 milligrams. And so therefore we were safe in not having to do a like we said here, a third run of the heating cycle. All right. So my next goal is to start calculating these things here. So what I'm going to do is I'm going to put numbers here on these items. So I'm going to call this number 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and 21. Now here's what I would do if I were you. At this point, you will have received a sample set of data with a mock unknown. If I were you, what I would do is I would go through these calculations with your numbers and follow along as I do mine. Of course, you can always simply follow mine with these numbers that are here from my student Susan's, and then you can go back and do your calculations. Please await instructions as to how we're going to require you to upload your lab report in the end. So for the moment, just follow along, perhaps with your own calculations. Okay, so the first thing I want to find out is what was the mass of my sample. So that would be essentially the difference between the full test tube and the empty test tube, which is items 2 and 1. Okay, so I'm going to come back here to my calculations page, and this is going to be item number 9. And this will be the mass of my sample. And again, this will be item number 2 minus item number 1, which in this case is 24.0792 minus 21.8372. And careful with sig figs. This should be a total of, 2.2420 grams. Okay, that's the number that I'm going to put in here. All right, erase that. Let me see if zooming this up will help me out here. Zoom in a little bit here. Okay, so I'm going to put in here 2 point 24. Okay, 2420. Gosh. Okay, I'm having some problems here with this technology. Please forgive me, but I'm going to keep on trying, and hopefully you can follow along, okay? I'm going to see if I can fix this guy here. Okay, wow. 4, goodness. Okay, I can do this. 2420. Yeah, it seems like the tip of this electronic pen, this stylus, is kind of like acting up. And it's giving me a lot of kind of weird stuff here. I don't know why, but I'm going to keep on trying because we got to use up our time. Okay, the next thing is to calculate the mass of the oxygen. Now remember, when we look at the chemical reaction that we're working with here, right? We said that basically whatever initial mass of potassium chlorate I had in here has now been converted into a mass of KCl and a mass of oxygen. The oxygen has escaped my test tube, so all I have left is the KCl. That means that whatever difference there is in mass between the product and the initial, that should have been equivalent to the mass of oxygen that escaped. So, coming back here to our data, oops, sorry, that's not it. Let me go back here. Coming back here to our data from Susan's thing, we can see that the difference between the mass of the test tube plus product and whatever mass you started with, right? That'll give you the total mass of oxygen, right? So what we're going to do is we're going to take your initial mass. I'm sorry, I probably said that in reverse. We're going to take the mass of test tube plus sample that we started with, and we're going to subtract the mass of the test tube plus the product. I'm going to use the final number here. So going back to my calculations here, okay, I'm going to work now on item number 10, which is the mass of oxygen. And like we said, that should be the difference between, in this case, the starting mass and the final mass, okay? So that should be, in our numbers here from Susan's, that would be 24.0792 minus 23.5732, and that equals 0.5060. All right? So that's going to be the number of grams of oxygen that we have. And I'm going to come back here, and let me get this out of here and come back in here, and we're going to write down this 5060 grams. Since the units are already indicated here on the left side, I don't need to repeat them in my data here, okay? So that's my mass of oxygen. Okay, now comes the interesting part, which will take care of the first item in our goals, in our objectives, all right? So let me come back here to our calculations. What we're going to do now is we are going to try to calculate what is the mass of potassium chlorate in my initial sample. So to do that, let's remember what the equation was, right? So this is item number 11. So our equation was 2KClO3 reacting to form 2KCl plus 3 units of oxygen gas. Now, this tells me that for every 2 moles of potassium chloride that decompose, 3 moles of gas are produced. So I'm going to use that ratio, but again, like in stoichiometry, we have to do this transaction in moles, but the units that we've been given are in units of grams, so we had to do the conversion. So starting with 0.5060 grams of oxygen, we had to convert that into moles. So 1 mole of oxygen is, remember this is O2, so that's 32, not 16 grams of O2. According to the equation, 2 moles of KClO3 are decomposed to produce 3 moles of O2. And we can cancel those out. And if you had time, you can calculate what is the molar mass of KClO3. I'm not going to show it here. You are able to do that. It's 122.55 grams, all right, of KClO3 for every mole of KClO3. All right, so that's where we're at right now. And you plug in those numbers in the calculator, The moles of KClO3 are going to cancel out, and this gives me a total of 1.292. Remember that because in here the initial mass of oxygen only has 4 sig figs, we can only round this to 4 sig figs, so it'll be grams of KClO3. So let's take that number and bring it back here to the data sheet. And over here, I'm going to put in 1.29, oops, kind of acting up again. Okay, 1.2, wow. Okay, let me see if I can make this happen here. 292 grams of potassium chloride. Remember, our first objective in the experiment, right, was to find out what was the percent of potassium chlorate in our mixture. So now that we have the grams of potassium chlorate, we can come here and calculate what is the percent potassium chlorate in our mixture. So this will be item number 12, percent of KClO3. So that's going to be, we have 1.292 grams of KClO3. And our initial sample we said was 2.2420 grams of sample times 100%. And we can calculate that. Again, it'll be limited to 4 sig figs, and that comes up to be 57.62%. And that is what we're going to write down here in the percent KClO3, 57.62%. Of course, when you do your second trial, you'll have a second value for the percent of chlorate, and so you'll have to calculate the average and put it in here, okay? I don't have Susan's second trial data here, so I can't do that for you, but you should be able to simply calculate the average of those two. Okay?
Okay, students, please accept my apologies. I'm switching over to a paper version of our calculations. The video that we were trying to use was full of glitches, had too many problems, and rather than continue to frustrate you, I figured we'll just do the rest of it here on paper. Please accept my apologies. We still have continuity. So far, we have taken the data from my former student Susan, and we've calculated all the way through the percent of potassium chlorate in her unknown mixture. As we said, there would have been a second trial, and she would have gotten a second value here, but it seems to have disappeared. It's completely invisible. So we're going to go on and continue with our second goal of the experiment, which was, let's see what we arrive at in terms of the molar volume of a gas at standard temperature and pressure, or STP conditions. All I did here for now was I copied over the mass of oxygen that we determined to have, 0.5060. And our next step is to find out, well, how many moles of oxygen was that? Notice that we're doing this calculation on the basis of stoichiometry, right? So let's go ahead and go to our second calculations page here. Once more, if you were doing this on your own, you'd want to do it in pencil so you can erase mistakes. I'm doing it in marker because it comes up better here on the screen on my camera. So this is going to be now item number 15. We're going to calculate the number of moles of oxygen. And of course, that would be the mass of oxygen, which was 0.5060 grams, times the molar mass, 1 mole, well, actually divided by the molar mass. And remember, this is O2, so it's 32 grams per mole. That cancels out that. And we have over here a total of 0.01581 moles. Again, we're going to 4 sig figs. So this is the number of moles of oxygen that we have. And what I'm going to do now is, if you don't mind, I'm going to pull this paper out so I can write that number over here, 0.01581 moles. Okay, our next step is to find out, remember that we're doing this under conditions from our experiment. So we want to find out, well, in our conditions, what was the volume per mole under our conditions? Well, we have a volume here of 392 milliliters of water, which we are saying, well, that's the equivalent of the volume occupied by the oxygen. So let's go ahead and write here, we're going to calculate number 16 here. That'll be the volume. And typically we use a bar here to indicate that it is the volume for 1 mole. So this would be item number 8 converted to liters, right? So item number 8 converted in liters divided by the number of moles, which we just calculated in item number 15. So let's see what that is. We had 392 mLs, but converted to liters, that would be, let's say 10 to the minus 3 liters is 1 ml. And we're going to divide that by the number of moles we have here, 0.01581 moles. Milliliters are going to cancel out. And let's see what we get with that. Let's go ahead and do the calculation here. So we have 0.392 liters divided by 0.01581 moles. And that gives us 24.794439. We are limited to 3 sig figs here because of this measurement. So we're going to have to round this to 24.8. And this would be liters per mole. Now remember, this is what we're obtaining under the conditions of our experiment. So this is not the final answer that we're looking for, but we're going to write it here in item number 16. This will be 24.8, and this is liters per mole. It's already in there, so we don't need to repeat the units. Now remember, our task is to find out, well, what would be the volume of 1 mole of gas at STP. To do that, we had to do some conversions here. For example, we want to switch units here. So let's go ahead and we also want to make sure we adjust. For example, let's look here. Item number 17. We're trying to find out the pressure that we have here, the total pressure that we equalized, represents the pressure of the oxygen plus water vapor. So we need to find out what the pressure of the water vapor is so we can adjust the total to find the pressure of the oxygen. So this is item number 17. And we're going to get this pressure of H2O from our table. So we had to find that table in our books. I apparently don't have it here with me, but you can find it there in your handout. And what is interesting is the temperature that we register here was 24.5 degrees. So it's between 24 and 25 degrees Celsius. So that is a very small interval. So let's do this. Let's assume that within that interval, the vapor pressure of water would be increasing linearly. And so we're kind of halfway in there. So what I'm going to do is I'm going to take the half point. In other words, the half point between the pressure at 24 degrees and the pressure at 24. It's kind of like calculating the average. So 22.4, which is the pressure at 24 degrees. 23.8 is the pressure at 25 degrees. I'm going to find the midpoint of that. And this comes up to be 23.1 torr. In many cases, your temperature would have been right on the mark, 24 or 25. So, the temperature. And so you'd be able to just read the vapor pressure of water straight off the table. But in our case, we had to do a little manipulation here. So we said this is going to be 23.1, again, units of torr. So now we can calculate what was the partial pressure of just the oxygen. This is item number 18. What is the vapor pressure of just the oxygen? Well, that would be the total pressure, which is item number 6, minus the vapor pressure of water. So item number 6 minus item number 17. So that's 7 58.5 torr minus 23.1 torr, and that is 735.4 torr. And that is the pressure exerted just by the oxygen gas that we harvested. Excuse me. Let's write it over here. 735.4 torr. The next thing we want to do is we want to find out what is the temperature, but we have to change it to Kelvin. Remember, when we work with gases, we have to use the absolute scale. So this is item number 19, and this would be the temperature of the oxygen. We assume the temperature of the oxygen was the same as the temperature of the water over which it was sitting. So that's 24.5. And we add 273.15. Our result has to be rounded to 1 decimal by the rules of sig figs. So this is 297.7 Kelvin. Don't forget, we don't say degrees Kelvin. It's just Kelvin. Okay, let's copy that number over here. We're almost there. We're almost there. All right, so this is 297.7. And now comes the crux, the highlight of our calculations. We have the volume of 1 mole of gas at this pressure and this temperature. What would that volume be under conditions of STP? So this is going to be our item number 20. And for that, we are going to use the combined gas law, P1 times V1 over T1 equals P2 times V2 over T2. And remember, the idea here is that these are the conditions under which we did our experiment. So this is the lab, and these are the conditions at STP. And what we're trying to find is what is the V2 in this case, the volume for 1 mole. So let's go ahead and rearrange this whole equation here. It would give us, let's see, I can have space here, V2. And I'm going to go ahead and put a bar in there because we're saying this is for 1 mole. So this would be pressure at 1 times the molar volume at 1. And then we clear out T2 over here. And then over here we have T1 times P2. And we have all these numbers available to us. Let's go ahead and see what they are. Okay, we said the pressure of our gas under our lab conditions was 735.4 torr. Sorry about that. See, the marker is a little too thick and it kind of hard to write on it. Then we have the volume we determined to be 24.8. This is liters per mole. And then we have the temperature 2, that would be at STP 0 degrees Celsius, which is 273.15 Kelvin. Okay, so we had the top part there. Now we're going to divide all of that by T1, which is the temperature at which we did our experiment. That would be 297.7 Kelvin. And P2 would be the pressure at STP, which is 1 atmosphere. But since we're using torr, we're going to convert that into torr. We'll make it as exact as we need to because it is an exactly defined relationship. Let's make sure the units cancel out. So I got torr here. I got Kelvin there. And so when I do this calculation, I'm going to end up with units of liters per mole. My least precise value here is exactly that calculation of the liters per mole, and it has 3 sig figs. So when I put all these numbers in the calculator, I get 22.0 rounded to 3 sig figs liters per mole. That's what we're getting. So let's go back and put this over here in our data sheet. So we're getting 22.0, again, liters per mole. So our last step consists of finding out, well, what is the percent error here? Let me put this up a little bit here, just make sure we can see it. Our last step is to find out what is the percent error. And you might have forgotten how to do that, but this is again item number 21, percent error. The goal here is to find out how close were we to the actual reported value. So this would be the absolute value of, let's say, our experimental result minus the actual value that it should be, in other words, the reported one, divided by the actual real value. We could say real instead of actual, but I like actual because that's kind of like a fact, times 100%. In other words, it's an observed fact, not like an absolute truth, so to speak. So let me pull this up a little bit here, and let's put the numbers in here. So the value that we obtained was 22.0. The actual reported value for 1 mole of gas at STP is 22.414 liters per mole. That is what is recorded in the literature. That is the value that we sort of like, quote unquote, challenged or questioned, or we're trying to confirm, so to speak, times 100%. So let's go ahead. Let me bring my calculator over here. Let's do that very quickly here. And let's see. Let me put it up here so you can see it underneath. So I have 22 minus 22.414. Of course, it comes out negative, but I'm going to go with the absolute value, say 0.414. Okay, notice that number has 3 decimal places, but our input value only had 1. So technically, we can only count the 0.4 up to there. That's as far as we can go in terms of precision here. So that means that into the next operation, although I'm not going to round it now, we're only bringing in 1 sig fig. All right, so I'm going to divide by 22.414 multiplied times 100, and we get 1.845. But because I am limited to 1 sig fig total, because there was only 1 decimal allowed up here, that means that this is going to be rounded to 2%, right? 1.8 rounded to 2. And that is the value that I'm going to put down here in Susan's data sheet. Coming back here, we're going to write this at 2%. Not bad, huh? That's pretty close. Normally, in many of my classes with students doing these things, it's the first time they ever do it. I allow them to have up to about a 10% error, and I'm good with that. But this is very good. Like I said, she would have had another set of data here and another set of numbers, not required to show the calculations for the second trial. Of course, you can put them in there just for your own records later on if you want to use it to study with. She would have found another value here for the volume of oxygen, another percent error. And then what I will do is when I grade it, I will look at what was the percent difference between the two results. How reproducible were the results that Susan found or any student found here. Okay, now remember, you're going to be receiving a data set that already has the numbers here, and based on that you will fill out the rest of the data sheet. You will have to show your calculations separately, and you will have to arrive at a value for the molar volume of oxygen at STP according to your data, and also identification of the percent KClO3, which I will check against my records and see how accurate your determination was. All right. Again, I apologize for having to switch over to paper, and because of the glitches we had in the digital or / electronic version of this presentation. But hopefully this will work, and hopefully you can go on and do your lab report. All right. Don't forget to follow the instructions and submit your assignment via the assignment box in Canvas. Thank you very much.